Okay, so now we are going to start the next module, which is module 8. It's on heap. Now, heap is also a binary tree. So, we're looking at binary trees. We start with the general binary tree and then we focused on binary search tree. So, now we are going to look at another variant of binary tree, which is called a heap. So, now in order to call a binary tree as a heap, two important properties need to be satisfied. Okay, so the first property is, of course, it has to be a binary tree, right? So what kind of binary tree it has to be? It has to be what is called an essentially complete binary tree. So now what is an essentially complete binary tree is? So now we all know what the height of a binary tree is, right? So the height is the maximum distance from the height is nothing but what? The length of the longest path from the root node to a leaf node, right? So the height of this binary tree is 3 because the length of the longest path from the root node to a leaf node is this, which is also nothing but the maximum level number. So the maximum level number is 3. So that's the height of this binary tree, right? So a binary tree of height h is essentially complete if it is a complete binary tree up to the level h minus 1. So, so in this case, the height of this binary tree is 3, right? That's the maximum level number. Now, 1 less than that height, which is h minus 1. So 3 minus 1 is 2. So this is level 2, right? So the binary tree is a complete binary tree up to that earlier level, h minus 1. So if you just look at the binary tree only up to this level, don't consider these 3 nodes in the last level. So just consider the nodes up to level h minus 1, just this thing. It is a complete binary tree, right? So that is one part of the rule. It should be a complete binary tree up to level h minus 1, and the nodes at level h are as far to the left as possible. So nodes in the last level are as far to the left as possible. Okay, so you'll know why this rule is stated like this, because let me show you one more case. Let us look at this binary tree. Now, the first part of the rule is the nodes up to the last but earlier level, which is up to this level, they will form a complete binary tree. But the nodes in the last level are not as far to the left as possible. So we see you have these nodes here, and then this node in the earlier level is like a leaf node, and then these nodes have 2 child nodes. So these nodes are not to the left as possible. Okay, whereas here, yes, in the last level the nodes are as far to the left as possible. But I say this is also not an essentially complete binary tree. Why? There are 2 rules to be essentially complete. The first rule is what? The nodes up to the level before the last level should form a complete binary tree. Now this is not a complete binary tree up to level h minus 1 because this node is missing a right child. So it's not a complete binary tree. But in the last level, the nodes are as far to the left as possible. That's fine. So both rules should be satisfied. So the nodes up to level h minus 1 should form a complete binary tree like this. And in the last level, which is level h, the nodes should be as far to the left as possible. So if both these rules are satisfied, that binary tree is an essentially complete binary tree. Okay. Now later we are going to see how to check if a binary tree is essentially complete or not, and that could be an assignment too. So now one thing that we can also say is a complete binary tree, which we all know what it is, right? We all did an assignment or doing one right now, is one where every internal node has 2 child nodes. So this is a complete binary tree. Now a complete binary tree is essentially complete because it implicitly satisfies the definition. The nodes up to the level h minus 1 form a complete binary tree, and all nodes in the last level are as far to the left as possible. This is the best we can do to arrange all the nodes at level h. right? So complete binary tree is essentially complete. Okay. So far we just looked at when can we call a binary tree as essentially complete. So now what we are going to see is when can we call a binary tree as a heap, right? So a binary tree is a heap if these two properties are satisfied. The first property is the binary tree has to be either essentially complete or simply complete. And in addition to that, we are going to also deal with data now. So the nodes have data, and the data of the nodes should satisfy this property. And accordingly, we can say a heap is either a max heap or a min heap based on the data. So the rule for a max heap is this: the data for every internal node should be greater than or equal to the data of both its child nodes, the immediate child nodes. So like in this case, 10 is greater than or equal to both its two immediate child nodes, in this case 8 and 9. So it could be like 10, 10 and 9. That's okay. That's also satisfied. So the data for any internal node should be greater than or equal to the data of its immediate child nodes. So in that case, and again, this should be applicable for all internal nodes. So 8 greater than 5 and 6, 9 greater than 1 and 7, 5 greater than or equal to 5 and 4, 6 greater than 3. So both the child nodes. Okay. So if the data for any internal node is greater than or equal to the data of both its child nodes, then and also the binary tree is either essentially complete or complete, then we can call that binary tree as a max heap. So this binary tree here is a max heap because again you can check the nodes up to level h-1 form a complete binary tree, and the nodes in the last level are as far to the left as possible. And then for the data for every internal node is greater than or equal to the data of its two child nodes. Okay. Now we can also have something as a min heap. Again, a min heap is a binary tree which is either essentially complete or complete. Now with regard to the data for every internal node should be less than or equal to the data of its immediate child nodes. So 1 less than or equal to its two child node data 3 and 7. 3 less than its two child nodes 5 and 4. Now you could think whether it should be like always the left child data is greater than right child. No, not necessarily. Like you see here, this is 5 and 4, whereas here this is 8 and 9. So it's okay either way. So the rule is just this: the data for the internal node should be less than or equal to the data of both its child nodes. So we don't need to worry about how the data of the two child nodes are. Okay, the left child could be less than the right child, or the left child could be greater than the right child. That's okay. So again, the data for this internal node is less than or equal to the data of its two child nodes, and the data of this internal node is less than its data of its left child. So this is again essentially complete because it's complete up to the earlier level h-1, and the last level the nodes are as far to the left as possible. So that should be always satisfied. That's essentially complete or complete. Then we have to check with just the data of the nodes. Accordingly, we can call it as a max heap or a min heap. Okay. All right. So now you kind of could get confused, but should not get confused. What is then the difference between a binary search tree and a heap, or like max heap or min heap? Now just put things together. What is the difference? In a binary search tree, the rule is what? The data for the internal node should be greater than or equal to the data of its left child, and less than or equal to the data of its right child. So 7 greater than or equal to its left child data, 5 less than or equal to right child data, 9. Whereas for a max heap, the data for the internal node should be greater than or equal to both its child node data. Okay, so 10 greater than or equal to both 8 and 9. So that's the difference between a binary search tree and a max heap. Or you can also say min heap, right? So should not get confused between the two. They're entirely different type of binary trees. So again, let me repeat: in a binary search tree, the rule is the data for every internal node should be greater than or equal to the data of its left child and less than or equal to the data of its right child. That's a binary search tree. Whereas for a max heap, the data of an internal node should be greater than or equal to the data of both its child nodes. Okay. Similarly, for a min heap, the data for an internal node should be less than or equal to both its child nodes. Okay. So now we can use the thing that we saw in the last module, the property or the procedure, how to convert one binary tree, some arbitrary binary tree, to a binary search tree by preserving the structure. So let us say now we are given a max heap, which is a binary tree. Okay, and the max heap has the structure in this example. Now we want to convert this max heap, a binary tree, to a binary search tree by preserving the structure. But what we have to rearrange the data. So we have to rearrange the data of this max heap so that we get a binary search tree. So how to do that? We know how to do by now. What we have to do? We have to do an in-order traversal of this binary tree, right? So the max heap is a binary tree, so we'll do an in-order traversal of this. So when you do an in-order traversal of this, start with the root but don't list it, go to its left subtree, go to its left, go to its further left, so 7 and the corresponding data 5. Then go to the root, so node 3 and corresponding data 5. Then go down the right subtree, node 8 and the corresponding data 4. Then with the left subtree, go to the root, node 1 and the root the data 8. Go to the right subtree, the root is 4 and the data, so of course we should not list the root, we have to go to the left subtree, so the root is 9 and 3. Then go to this root 4 and 6. Then done with the left subtree, go to the root which is 0 followed by the data 10. Then go to the right subtree, don't list this one, go to its left subtree, so node 5 followed its data 1 and then 2 its data 9, then 6 and 7. So this is the listing of the node IDs and the corresponding data when you do an in-order traversal of this max heap, a binary tree. So now what you do is you sort the data, just the data. Don't do anything with the order of the node IDs, let them be as it is. Just sort the data of the nodes. So when you sort them, you're going to have 1 followed by 3, then 4, the 2 5s, doesn't matter how you write it, just write this 5 followed by this 5, then 6, then 7, 8, 9, 10. So this is a sorted order of the data. Then what we do, just superimpose for these nodes, write the corresponding data. For node 7, the data is going to be 1. For node 3, the data is going to be 3. Then node 8, the data is going to be 4. Then node 1, the data is going to be 5. Then node 9, the data is going to be 5. Then node 4, the data is going to be 6. Node 0, the data is 7. Node 5, the data is 8. Node 2 is 9. Node 6 is 10. So this is now a binary search tree. You can cross check. Of course, we just built it from the property that if you do an in-order traversal of this binary search tree, you're going to get the data of the nodes in the sorted order. Okay, so this is how you convert a max heap to a binary search tree. So you're given a min heap, which is also a binary tree. We can do the same process and convert to a binary search tree. Okay, so let me stop for a minute.